Helen Rear from the University of Utah. Her work is about lead feldspars, and she's evaluating the reference materials and methods for lead isotopes in potassium feldspars. What is the application for detrital provenance?
Thank you, Lillian, for the introduction. And we're just about a minute early, so hopefully that's all right to go ahead and get started. So my name is Ellen Reat. I'm a PhD candidate at the University of Utah, and I work with Carrie Johnson. And I'm going to talk to you today about a portion of my PhD where I'm applying detrital potassium feldspar lead isotopic ratios to provenance questions in southern Utah. So first, I really want to put this study and the motivation in context for you. The rocks in question here are from the John Henry member of the Straight Cliffs Formation, which outcrops in the Kaiparowits Plateau of southern Utah, which you can see. Can you guys see my pointer?
No, not yet.
Okay, what about now?
Oh yes, now we see it. You can see it.
So Kaiparowits Plateau here in southern Utah. And these strata are part of a prograding clastic wedge sequence that transitions up section from a dominantly fluvial system to a fluvial and shallow marine system. And many other students before me have collected a large amount of data from this area, sedimentological evidence, facies correlations, paleocurrents, and also a lot of detrital zircon uranium lead geochronology data. The sandstones in this unit are mostly subangular quartz and potassium feldspars, which is one line of evidence that the main sediment source for this is a proximal exhumed granitic source, and that the dominant paleo flow from thousands of measurements here is basically southwest to northeast. In the previous detrital zircon studies, we've seen that the major contributors of zircon to the basin at the late Cretaceous time, the time of deposition, are the Yavapai Mazatol granites from the Mogollon Highlands of northern Arizona, down here. That's roughly 70% of the grains that people have analyzed. Then secondarily, Jurassic and Cretaceous aged grains from over here in the Cordilleran Magmatic Arc, that's about 12%. And then a similar about 12% source attributed to the severe fold and thrust belt recycled strata, so coming from the west here. All of this together points to major sediment sources being located dominantly in the southwest and this northeast paleoflow direction in addition to the sedimentological data. So this implies that what's generally assumed to be the main accommodation control, flexural loading of a prograding fold and thrust belt, is actually possibly decoupled from the main sediment flux, which is tied more to the exhumation of these southwestern sources. This is the context of my work with potassium feldspars and lead isotopes. There's still some uncertainty here as to the relative proportions of each of the sediment provided by each of these source terrains. This is in part because the severe fold thrust belt is predominantly composed of recycled sediments, and this can make it really challenging to attribute sand grains directly to it as a sediment source terrain. We also wanted to know if the second provenance indicator, lead isotopes and potassium feldspars, could add to this story and help us extract the influence of the recycled severe sediments from our first cycle sediments, which we would think maybe would be coming from these exhumed granitic sources or these volcanic sources over here to the west. So why potassium feldspars and lead isotopes? There's a number of reasons that these can be useful in provenance studies. First of all, potassium feldspars are less likely to survive more than one cycle of exhumation, transport, and deposition. Both physically and chemically, they are softer than zircons, which is our main geochemical provenance indicator that folks use now. And so we typically would be expecting to see far fewer recycled detrital feldspars than we would zircons. Potassium feldspars are common in classic rocks, particularly in contrast to heavy minerals like zircons. And because potassium feldspars reflect the basement lead domains from where they originated, which is kind of at a suborogenic scale, you actually don't need as many feldspars in a sample in order to characterize all the possible sediment source terrains, because there are fewer specific locations and specific ages that these things could be coming from. Typically right now it's about 40 grains per sample is considered enough to characterize a sediment source terrain that's about 10% of the input there. And like I said, feldspars reflect the lead domains of their sediment source rocks. That's what this diagram here is showing you. It's illustrating that if you have this fluvial system that's sourcing sediment from here, from here, from here, that you're going to see lead domains that reflect each of these regions represented in your feldspar lead isotopes. And there are 4 isotopes of lead that we look at: 208, 207, 206, and 204. 208, 207, and 206 are all the result of decay systems, they're radiogenic, and then 204 is stable and non-radiogenic. And so when we present this data, it's typically in ratios of these isotopes to each other. So we know this works as a provenance indicator. It's been shown in a number of different areas that it works, but we want to know if it works in the Cretaceous Western Interior Seaway and the Kaiparowits Plateau. When we began investigating how to collect this data and analyze it, we ran into a couple of concerns right away. Because this technique is relatively new and underutilized, only really starting to be used in the last few years, there's only a few labs in the world who do this type of data collection, and because of the way it's developed, everyone does it a little bit differently. And we use different reference materials, different data collection techniques, different error propagation methods, and different ways of displaying the data. We're also applying this to disaggregated small sand grains, which is a new application. And so we needed to make sure that we were able to measure these isotopes accurately. So when we were starting to try and analyze this, we were realizing that there's not a good set of standard reference materials like there are for detrital zircons kind of accepted in the community. And so we wanted to test different possible reference materials that other people have used, in addition to some new ones that we collected, to see if we could really establish, the best practices for standard reference materials, and then also characterize them well enough to put this data out into the community so that others can use this as well. And what we found was that feldspars, in some cases, have inherent chemical and physical heterogeneities, and this does matter when we choose a standard reference material. So you can see over here on the left are 3 plots where I'm illustrating the same set of data. So all of these colored dots are the same set. They're, in this case, they're data collected from the Shap Feldspar, which is from the UK. In teal is the Fish Canyon Tuff, those are sanidines, and the orange is NIST glass, which is a man-made glass. What I'm showing you is these same set of analyses 3 times, standardized to different reference materials. In this case, NIST 612 is the standard reference material. The Fish Canyon sanidine is a standard reference material here, and the Shap orthoclase is a standard reference material here. You actually get dramatically different values for these data depending on what you use as a reference material. And if you do geochemistry, you know that this is kind of a big deal. If you use a different standard reference material for one study and another, your data may not actually be able to be compared. And in provenance work, that's really important. We need to be able to compare different provenance data sets to each other. And this, like I said, is likely the result of either chemical or physical heterogeneities. Some of these things can actually cause laser ablation issues, meaning that the laser, under the same analytical conditions, will ablate different materials differently. This can cause changes in signal strength, and it can also cause some of these variations in calculated ratios. And so as a part of this, we also wanted to test the ablation behavior of each of these materials. And that's what I'm showing you here on the right. We ablated each of these a number of different times under the same conditions. And what we found is that the sanidines, the Fish Canyon and the Marysville, which is a local Utah sanidine, actually seem to respond significantly better to ablating than the orthoclases, little Cottonwood from here in Utah and the Shap, as I mentioned, from the UK. what we see is there's significantly less heterogeneity in the ablation response from both Fish Canyon and Marysvale than there is from Little Cottonwood. Even Little Cottonwood here, you see some shattering, maybe along cleavage planes, and then you see a lot of pit irregularity. And what that's telling us is that that we know that sanidines now are a little bit better behaved physically to ablation. And then over here, what we're getting from this is that our sanidines, our Fish Canyon here in teal, and our glass, our man-made glass, are significantly better behaved than our orthoclays as far as a standard reference material. So chemically, they're better behaved as well. And so now that we feel good, that we understand our method and the right standards to use, we want to apply this to the system, and we want to compare it directly to detrital zircon data to see what the difference in provenance signals are between these two provenance indicators. So what I'm showing you here is new data we collected, detrital zircon data. And we did this because we wanted to make sure we were comparing the exact same rocks, the feldspar signal and the detrital zircon signal, rather than just comparing to the bulk of literature that's out there. And what we see in our new detrital zircon samples is not surprising. It basically aligns with what has been previously interpreted for the entire Kaiparowits Plateau. We see a very strong Yavapai Mazatzal southern sediment source. That's this red peak here. We see a clear Cordilleran Arc source, that's this blue peak here. We see some severe recycled sediments, which are in the Appalachian and Grenville sort of age ranges. And we also see a very small, but still present, Archean source here. And this could be recycled from the severe fold and thrust belt, or it could also be, has potentially attributed to northern longshore drift coming from north to south within the seaway. I'm just showing you the relative proportions here. You can see it does change stratigraphically, but we do see a real dominance of that Yavapai Mazatzal source. We see a really strong Cordilleran source and then kind of a varying severe recycled source through there. So this is what we expected from the zircons, and we want to compare it to our feldspar data. So when we plot the feldspars from the same exact samples, the story changes a little bit. What I'm showing you here on the right is our detrital feldspar data plotted in lead-lead space. So 208 to 206, that ratio here, 207 to 206 here. And what you can see is at least 3, maybe 4 nice, clear populations illustrated. And then there's quite a few outliers around these, but you can see that there's these dense areas where we see groupings of specific isotopic ratios. So this is great. This means we likely have multiple sediment sources contributing feldspars to our strata, but now we need to be able to pin them to where they came from. And this is where things get a little bit trickier too with feldspars, because it's a newer technique. There's just not as much sediment source terrain data out there. But there actually is some out there in the literature. There's some from feldspars, there's some from ores, and there's some from whole rocks. What I've done is I've collated a database for North America with lead data from all of the literature I could find for all of these different rock types, and then plotted them here. As you can see, this is just feldspars, but as you can see, there's quite a bit in the Western US, which is good news for me. But there's kind of a dearth here in the central US. Part of this is, much of this is covered in sediment, so it's hard to get basement rock samples, although you can see there's some up here. And so I say, okay, I've got this database, I have all these literature datas, let me plot those into the lead regions we might see. And this is what you get. So over here, I'm showing you the same lead-lead space that we were just looking at. I'm showing the density diagrams of where each of these terrains lead ratios are. So what I've done is I've categorized all of the lead data out there into terrains based on location and age, and then grouped them here. So you can see down here, we've got the Mojave terrain reflected here in purple. We've got our Western Cordillera, this nice blue one. Wyoming is a little bit more spread out, this Northern Archean source. That's kind of interesting. And then we also have a grouping of the Yavapai Mazatzal, our southwestern source here. And then the pink and the green are Appalachian and our Grenville signals. And these are what we would attribute to being recycled within the fold and thrust belt strata. So this is our map. This is what we're looking at. This is our source location. So what we want to understand is, based on our feldspar data and our zircon data, what does the system look like that's transporting sediment here? When we overlay our detrital data on top of those polygons, it's a little bit of a busy diagram, but you can see that these four populations still really pop out, and they overlap significantly with this Western Cordillera, the Wyoming terrain, and the Yavapai Mazatzal terrain. There are a few sprinkled here and there that overlap with what we would call the Appalachian, the Grenville, some in this Mojave. But for the most part, our data are concentrated over the Western Cordillera, the Wyoming, and the Yavapai Mazatzal terrains. We don't see a strong Grenville or Appalachian signal, which leads me to believe that there's a lack of this severe fold and thrust belt recycled signal. And this kind of makes sense to us, right? Because we would not expect feldspars to survive significant recycling and be included in here, whereas we do see that signal in zircons. There is some spread where we don't have a source terrain attributed to it. This is possibly that source terrain no longer exists. This could also just be, analytical spread from data collection. Or there could be alteration that happens. There's different types of alteration that can happen to lead ratios in feldspars due to hydrothermal events or tectonic events over time. So what does this mean for our provenance interpretation? It means we agree with the zircon data that we have a strong signal coming from the west and southwest, as you can see in yellow here. We see very little influence of the severe fold and thrust belt, the recycled sediments, because feldspars probably don't survive recycling as well as zircons. The zircon signal here might actually be amplified due to their persistence in the geologic record. And so probably somewhere in between the two is the actual relative contribution of sediment from the severe fold and thrust belt. We also see this pretty significant input of our Archean Wyoming terrain. And this is kind of exciting because we don't see it in the zircon record. There is some sedimentological evidence from this location and others in southern Utah that there's quite a bit of longshore drift coming from the north, transporting sediment along the paleo shoreline there. And zircons being transported this way may be lost due to hydraulic fractionation. There's some evidence that because zircons are heavy, that they actually are not transported in the same way that lighter grains like feldspars might. And the other conclusions here are that we can measure detrital feldspars, lead and detrital feldspars, well enough to apply it to these provenance problems, particularly where recycling or complex sediment transport dynamics are a major factor. It's really important to use more than one mineral phase because of all these effects that we've talked about can affect your provenance signal. And the other conclusion here is we really need more lead domain terrain data. We need to understand all of these different possible sources. Because we just don't have as much as we do with zircons, it's harder to interpret these systems using only the feldspar data. So with that, I'll take questions and thanks to all the folks that have helped and all my funding sources.
Thank you, Helen. So if you have any question, please write it in the chat, or if you want, just raise your hand and we will let you to make the question. I find it fascinating what you have done here. And do you know if there are any other lead domain maps that has been done in the same area or maybe nearby?
Yeah, so the maps that I built are a compilation of all the data I was able to collect. There have been two other people that I have found who have who've built maps like this for the Western US. But they were focusing on different study areas. And so Like in particular, one was focusing on the Mississippi. So basically all of the Southwest US is covered by a legend. But yeah, so there's just not as much out there as you might imagine. And there's not as much as with the zircons for sure. There are other maps out there, and there's been some application of this work in Australia and in Nova Scotia, where there are some maps. But for the Southwestern US, there's much less.
Nice. So if there is any other question, let me check it out there in this. Please don't be shy.
There's one question in the question box.
Yes. My database combining. Okay, I'll read the question. I was wondering if your database combining the Northern American lead and feldspar will be available in some database repository to be cited for future work. Yes, absolutely. As part of this paper that is currently in progress, the database will be published as supplementary material. So I hope that you use it. Please use it. Apply this to future work. That would be great to see this really take off and to build that database out there. As we start to build our interpretations of strata, of detrital rocks that have these signatures too, it'll be really interesting to see if we can then even further piece apart recycling stories. Like if this rock is uplifted and recycled, we know what the lead signature looks like now. What would it look like if this is recycled into a different unit? So yeah, that database will be available hopefully later this year.
Okay, wonderful. So the question was made by Martin Nautzon, and he said, amazing, thanks for the answer.